Hi everyone, this is Christian Avery Malta, and for today's activity, I'll be doing my first video assignment in Eetvet 2. For number 1, it aims to describe the resistance in Ohm's law. So first, what is resistance? So resistance is a measure of the opposition to current flow in an electrical circuit, and it is measured in ohms. So Ohm's law, it is the formula used to calculate the relationship of voltage, current, and resistance in an electrical circuit. So first, let's have 1.1. How can you apply this in your actual installations? So we can use Ohm's law to control the amount of current in a circuit by adding resistors to reduce the current flow or by taking them away to increase the amount of current. Ohm's law is very helpful for us to minimize errors in doing actual installations. And also through Ohm's law, we can identify if nakulangan or nasubrahan ba ang atong supply sa particular na loads. And next, we have 1.2. What are examples of loads, conductors, and power sources? So for the examples of loads, we have three types of loads: the resistive loads, the inductive loads, and the capacitive loads. So for the resistive load, so it is consisting of any heating elements. So for examples are light bulbs, toasters, ovens, and even coffee maker. So next we have here inductive loads. Loads that power electrical motors are called inductive loads, mostly found in household items and devices with moving parts such as electric fans, vacuum cleaners, washing machines. And next we have capacitive loads. Example for this are the TV picture tubes and components used in electronic devices. Next is the conductors. So conductors is a material which permits the flow of electric charges. So for example, we have here the copper, aluminum, steel, cast iron, metal sludge. And next is the example for power sources. So power sources is a device or anything that supplies electric power to an electrical load. It may come in the forms of electric power grid such as electric outlet, energy storage devices such as batteries or fuel cells, generators, and even renewable sources. Next, we have here 1.4. What are the formulas involved? So first, we have here Ohm's law. And if we are looking for the value of the voltage, so we will use this formula, V is equal to IR. And if we are looking for the value of current, so I is equal to V over R. And for resistance, R is equal to V over I. We can also replace a V with E. And E is equal to the impressed voltage and the unit is in volt, or E or V na siya. I is equal to current drawn in unit is in ampere, and R is the resistance, unit is in ohm. For the next formula, we have here the resistance. So first formula for the resistance is R is equal to the resistivity times length over area. And also we have here, we all know that the formula for area is equal to A is equal to pi over 4d squared. And for the next formula is R is equal to resistivity times volume over E squared. So we will use this formula if the given problem has the given volume and the given area. So the next one is R is equal to resistivity times L to the power of 2 over the volume. And we also, so R is equal to the resistance and unit is in ohm. A, which is the cross-sectional area, which is in square meter. Resistivity is in ohm meter. Length is in meter and volume is in cubic meter. So we also have the effect of temperature in resistance. So first, it is like ratio and proportion. So R1 over R2 is equal to T plus T sub 1 over T plus T2. And next is the change in temperature is equal to T2 minus T1. And the next one is the coefficient of resistance is equal to 1 over T plus T1. So R1 is the initial resistance, unit is in ohm. R2 is the final resistance and unit is in ohm. T is the temperature when resistance of a given material is 0. T1 is the initial temperature. T2 is the final temperature. Delta T is the change. Next, we have here 1.5. Show sample problems and solve them. So first, we have here problem number 1. The substation bus bar is made up of 2 inches round copper bars 20 feet long. What is the resistance of each bar if resistivity is 1.724 times 10 raised to negative 6 ohms centimeter? So imagine that it is a round copper bars and it is 20 feet long and 2 inches in height. So for this problem, we will use the resistance, the formula for resistance, which is R is equal to resistivity times length over area, since we have the given length. And for the area, we will just substitute the formula for area, which is pi over 4d squared. So the final formula for this problem we will be using is R is equal to the resistivity times length over area, which is pi over 4d squared. So first, let's find the value of area. So since the given area is in inches, so we will convert that one into centimeter. So A is equal to pi over 4 quantity 2 inch times 2.54 centimeter over 1 inch is equal to 20.268 centimeters squared. And next, let's find the value for the length. So, and also, the length is given in feet. So, we will convert that one into centimeters. So, 20 feet and 1 feet is 12 inch and 2.54 centimeter in 1 inch. So, 20 feet times 12 inch over 1 feet times 2.54 centimeter over 1 inch is equal to 609.6 centimeter. So let's substitute the value of area and the value of length to our formula. So we will have R is equal to the resistivity, which is 1.724 times 10 raised to negative 6 ohms centimeter, times the value of length, which is 609.6 centimeter, over the value of area, which is 20.268 centimeters squared. So our resistance is 5.185 times 10 raised to negative 5 ohm. That is the answer for that problem. And for the next problem, we have here problem number 2. A load of 10 ohms was connected to a 12-volt battery. The current drawn was 1.18 amperes. What is the internal resistance of the battery? So it is our circuit. It is connected to a 12-volt battery, and it is our internal resistance, and it is our resistance. So it is a 12-volt battery, and it is our internal resistance, and this one is a 10 ohms. It is our resistance and current flow. And for this problem, we will use the formula. We will use this formula. I is equal to E, or the voltage, over the internal resistance plus the resistance. So since we are looking for the internal resistance, so we will just equate the formula. So our formula will become internal resistance is equal to E over I minus the resistance. So substitute the given to the formula. So we will have R is equal to the given volts, which is 12, over the current, which is 1.18 ampere, and minus the resistance of 10 ohms. So our internal resistance is 0.169 ohm. How the setup looks in actual application. So for this one, assuming that we have a regulator here. So by shifting the regulator to and fro, we can regulate the speed of the fans in our houses. We can do it by controlling the resistance via the regulator, and also the current flowing through the fan is also managed here through regulator. So for this one, mobile and laptop chargers. So they use DC power supply in the operation. DC power supply provides a variable output voltage based on the resistance, and the overall working is controlled by Ohm's law. So for number 2, describe magnetism and magnetic circuits. So what is magnetism? Magnetism is the force exerted by magnets when they attract or repel each other. What are the theories related to magnetism? So for this, we have electromagnetism. So electromagnetism is a type of physical interaction that occurs between electrically charged particles, sometimes called as Lorentz forces. which includes both electricity and magnetism as different manifestation but of the same phenomenon. So how is it related to electricity? Originally, electricity and magnetism were considered to be two separate forces, but this view changed with a publication of James Clerk Maxwell on 1873 about a treatise on electricity and magnetism, in which the interactions of positive and negative charges were shown to be mediated by one force. And now, electricity and magnetism are fundamentally interlinked. Flowing electrons produce a magnetic field, and spinning magnets cause an electric current to flow. Next is draw a magnetic circuit. So this is our source, or we will call this one as our MMF, or the magnetomotive force, and it is connected to our reluctance R that drives a magnetic flux to the circuit. So it is our reluctance, and this one is our reluctance, and this one is our magnetic flux, and the source is the magnetomotive force. In electric circuit, this reluctance R here is known as resistance, and this magnetic flux here is also known as I, or current, and this MMF here is known as EMF, or the electromotive force. Next, what are the formulas and verbs? So first we have here force is equal to the flux density times the current times length, where F is force, unit is in Newton, flux density, unit is in Tesla, current, unit is in ampere, length of conductor, unit is in meter. Next, we have here flux density is equal to flux over area, where flux density unit is in Tesla and the flux unit is in Weber. And the surface area perpendicular to the field unit is in square meter. So next we have here H for the magnetic field intensity is equal to N times current over the length. And H is equal to magnetomotive force over the length, where H is the magnetic field intensity, unit is in ampere torn per meter, mean length of flux lines, unit is in meter, magnetomotive force, unit is in ampere torn. We also have here magnetomotive force is equal to N for the number of turns times the current, where N is the number of turns. So next one is the free space permeability is equal to flux over the magnetic field intensity. So where U is the permeability of the material, unit is in Henry per meter. And next is the flux density is equal to free space permeability times the relative permeability of the core times current over 2 pi r, and the magnetic field intensity is equal to current over 2 pi r, where r is the perpendicular distance from the point, unit is in meter, and the free space permeability, the value is 4 pi times 10 raised to negative 7 and is a unit, but in centimeter gram second unit is 1, and the relative permeability of the core. Next one is the reluctance is equal to length over free space permeability times the relative permeability times area. And the other one, reluctance is equal to volume times length over area, where R is equal to reluctance, it is in reciprocal Henry, area is a cross-sectional area, and V for reluctivity. And the other one is the magnetic flux, or flux is equal to magnetomotive force over reluctance is equal, or also known as number of turns times current over R, since we all know that the magnetomotive force here is equal to the number of turns times the current. And NCGS unit, flux is equal to 0.45 times number of turns times current over the reluctance, where flux is in Maxwell and reluctance is in Gilbert per Maxwell. And for the next one, we have Show sample problems and solve them. So we have here problem number 1. Calculate the magnetic field intensity to produce a flux density of 10 times 10 raised to negative 3 Tesla at the center of a long straight solenoid. So for this problem, we will be using this formula since we have the given flux, which is in Tesla, and we are looking for the magnetic field intensity. So our formula is like this. Permeability is equal to flux over the magnetic field intensity. And also we can replace the permeability here with relative permeability times the free space permeability. So our formula will become magnetic field intensity is equal to flux over permeability, and change the permeability into this one. So our final formula for this problem is magnetic field intensity is equal to flux over the relative permeability times the free space permeability. So for this problem, we will assume that our relative permeability is in air. So our relative permeability, the value for our relative permeability is in 1. And we all know that the value of the free space permeability, which is in SI unit, is 4 pi times 10 raised to negative 7. So this one, we will be using this value for our free space permeability, 4 pi times 10 raised to negative 7. So let's substitute the given to our formulas. We get magnetic field intensity is equal to the value of flux density, which is 10 times 10 raised to negative 3, over the value of relative permeability, which is 1, times the value of free space permeability, which is 4 pi times 10 raised to negative 7. And our magnetic field intensity for this problem is 7,958 ampere turn per meter. And for the next one, we have here a coil with 900 turns is wound over a magnetic core with a reluctance of 10,000 ampere turn per Weber. If a current of 0.5 ampere is passed through the coil, how much is the magnetic flux that the coil generates? So for this problem, we have a given of turns, number of turns, given ampere, and given reluctance. And we are looking for the magnetic flux. So based on the given, we can assume that our formula for the magnetic flux, since we don't have a given magnetomotive force and we have a given number of turns and currents, so we will use the this formula. Flux is equal to the magnetomotive force over reluctance, and change the magnetomotive force into number of turn times current over reluctance, and plug in the given value to the formula. So that will become flux is equal to the number of turns, which is 900, times the current, which is 0.5 ampere, over the reluctance, which is 10,000. So for the magnetic flux that a coil will generate is 0.05 Weber, 0.045 Weber. How the setup looks in actual application. So we can apply magnetism in medical industry. So this one is called magnetic resonance imaging. So this part here filled with gradient coils, magnets, and also for this one sa appliances kanang sa DVD. So it is also filled with rotating magnetic disc. So for number 3, describe inductance and inductive components. What is induction? Induction is the process of generating electric current with a magnetic field. It occurs whenever a magnetic field and an electric conductor move relative to one another. So the conductor crosses lines of force in the magnetic field. What are the theories related to induction? So for this one, we have 2 theories that is related to induction. So the first theory is Faraday's law of electromagnetic induction. Faraday's law states that the rate of change of magnetic flux with time through the circuit is equal to the magnitude of the induced EMF in a circuit. So through Faraday's experiment, he formulated 2 laws of electromagnetic induction. So the first one is, whenever there is a change in the magnetic flux linked with a coil, an electromotive force is induced. 2. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux length with a coil. And for the other theory, we have here Lenz's law of electromagnetic induction. Lenz's law states that the polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. So this one, when magnet is inserted into the solenoid, a north pole will be induced on the right side to oppose the incoming south pole. So by right hand grip rule, the induced current will flow anti-clockwise. So this one, the direction of the current is in anti-clockwise. This one, when magnet is withdrawn, so withdrawn from the solenoid, a south pole will be induced on the right side. Ari na siya para ma-oppose niya ang outgoing north pole. And by the right hand grip rule, the induced current will flow clockwise. So the current direction for this one is in clockwise direction. How is it related to electricity? So it is related to electricity because electromagnetic induction has the ability to generate electric current with a magnetic field. Example for this are the electric generators and electric transformers. Both are using electromagnetic induction to generate electricity or change the voltage of electric current. So draw a circuit that involves inductive components. So for this one, I will draw a series connected inductor. So it is connected to a source. So this one is our L1 and the other one is L2. So this is our inductor 1 and our inductor 2. Formulas involved. So first we have here E is equal to length times di over dt, where E is the self-induced voltage and unit is in volt. L is the self-inductance, unit is in Henry. Di over dt is the rate of change of current, unit is in ampere per second. And the other formula is L is equal to N flux over I, and L is equal to N squared over reluctance, and L is equal to free space permeability times relative permeability times area N squared over the length, where L is the inductance, unit is in Henry. Free space permeability, we have 4 pi times 10 raised to negative 7 Henry per meter. And for the relative permeability of the core, reluctance of the magnetic path, reciprocal Henry. Area, cross-sectional area of the magnetic path, and unit is in square per meter. N is number of turns, flux is in Maxwell. L is the mean length of the magnetic path, and I is current, unit is in ampere. And we have also another formula. So this one is for mutual inductance. M is equal to free space permeability times relative permeability times area times N1 times N2 over the length. And other one, M is equal to K square root of L1 times L2. And the other one, M is equal to N1 times N2 over the reluctance, where M is the mutual inductance, unit is in Henry. L1 is the self-inductance of coil 1. L2 is self-inductance of coil 2. And K is the coefficient of the coupling. Series coils with, we also have formula for series coils with mutual inductance. So for series aiding, we have here, so the symbol for series aiding, we have here LTA is equal to L1 plus L2 plus the 2M. And for series opposing, LTO is equal to L1 plus L2 minus 2M. And the formula for mutual is equal to LTA minus LTO over 4. Where LTE is the total inductance, series aiding. LTO is the total inductance, series opposing. M is the mutual inductance between the two coils. We also have parallel coils with mutual inductance. So for parallel aiding, we have LTA is equal to L1 times L2 minus M squared over L1 plus L2 minus 2M. And for parallel opposing, we have here LTO is equal to L1 times L2 minus m squared over L1 plus L2 plus 2m. And next one, show sample problems and solve them. So for problem 1, what is the coefficient of coupling of two coils whose mutual inductance is 1 Henry and whose self-inductance are 1.2 and 2 Henry? So for this problem, we are looking for the coefficient coupling, and we have given inductance are 1.2 and 2 Henry. So for this problem, we will be using this formula, this one. So let's go back to our problem. So let's substitute the given. Let's plug in the given to our formula. So we are looking for the coefficient coupling. So our formula will become K is equal to M over the square root of L1 times L2. So our value for M is 1 Henry, is in 1 Henry, over the self-inductances L1 is 1.2 and the self-inductances L2 is in 2 Henry. So K is equal to 1 over square root of 1.2 times 2 is equal to 0.645. So our coefficient coupling for problem number 1 is 0.645. So for problem number 2, two coils of inductances 4 and 6 Henry are connected in parallel. If their mutual inductance is 3 Henry, calculate the equivalent inductance of the combination if mutual inductance assessed and if mutual inductance opposed, the self-inductance respectively. So first, let's calculate the parallel aiding. So parallel aiding is equal to LTE is equal to L1 times L2 minus m squared over L1 plus L2 minus 2m. So we all know that two coils of inductances are given in, we have 4 and 6 Henry, and their mutual inductance is in 3 Henry. So substitute the value to our formula. So we get 4 times 6 minus 3 squared over 4 plus 6 minus 2 times 3. So for our parallel aiding, we get 3.75 Henry. And for the parallel opposing, we have L1 times L2 minus m squared over L1 plus L2 plus 2m is equal to 4 times 6 minus 3 squared over 4 plus 6 plus 2 times 3. So for our parallel opposing, we get 0.9375 Henry. How the setup looks in actual application. So electric generators works in the principle of electromagnetic induction. So when the coil rotates, it cuts the magnetic field which lies between the two poles of the magnet. So the magnetic field will interfere with the electrons in the conductor to induce a flow of electric current inside it. So for number 4, describe capacitors and their construction. So first, what is capacitance? So capacitance is a measure of how well a capacitor can store electrical charges. So what are the theories related to capacitance? We have here electrostatics, and we have two laws of electrostatics. So the first law of electrostatics state that like charges repel each other and unlike charges attract each other, while the second law of electrostatics state that the force of attraction or repulsion between charges is directly proportional to the product of two charges and inversely proportional to the square of the distance between them. So how is it related to electricity? So it implies an associated storage of electrical energy. If electric charge is transferred between two initially uncharged conductors, both become equally charged, one positively, the other negative, and a potential difference is established between them. And also, through capacitor, we can create a magnetic flux, and we all know that magnetic flux is one of the requirements for us to somehow create an source of electricity like generator. So next, draw a circuit that involves capacitive components. So for this, I will draw a series-connected capacitor. So it is connected to a source. So it is our C1, and this one is our C2, our C3. So this is our C1, C2, and C3, and it is our source. So next is, what are the formulas involved? So first we have here C is equal to Q over E, where C is the capacitance of a charged capacitor, unit is in farad. Q is the charge stored, unit is in coulomb. E is the voltage across the capacitor. And other formula, C is equal to absolute permittivity times the relative permittivity times area over the thickness of dielectric material. And the other one is C is equal to dielectric constant times area over the thickness of dielectric material, where A is area of each plate, unit is in square meter. D is the thickness of dielectric material, unit is in meter. And K is dielectric constant, absolute permittivity, and this one is not absolute, it is relative permittivity. Sorry for that one. And you also have formulas for series connected capacitors. So for the total capacitor, it is total capacitor is equal to 1 over C1 plus 1 over C2 plus 1 over C3. And for the total charge, so total charge is equal to charge 1, charge 2, charge 3. They are equal. And for the voltage, the total voltage, so they are similar with the charge, so they are equal. Total charge is equal to E1 is equal to E2 is equal to E3. And we have also formula for parallel connected capacitors. So for the total capacitor is equal to C1 plus C2 plus C3. And for the total charge is equal to charge 1 plus charge 2 plus charge 3. And for the total voltage is equal to E1 is equal to E2 is equal to E3. Next, show sample problems and solve them. A capacitor consists of two similar square aluminum plates, each 10 cm by 10 cm, mounted parallel and opposite to each other. What is their capacitance in microfarad when distance between them is 1 cm and the dielectric is air? If the capacitor is given a charge of 500 microcoulomb, what will be the difference of potential between plates? How will this be affected if the space between the plates is filled with wax, which has a relative permittivity of 4? So for this problem, we have three unknowns. So there's the first one, second one, and the third one. So the microfarad here has an exponent of -6. Since they have the same exponent, so their exponent will become additive. So the microfarad will become picofarad. It is times 10 raised to -12. And we have the given distance, which is in centimeters. So first, let's convert that one into meter and also the area. So the given distance of 1 centimeter will become 0.01 meter, and the area of 10 centimeter by 10 centimeter will become 0.1 meter by 0.1 meter. And for the first unknown, what is their capacitance in microfarad when distance between them is 1 centimeter and the dielectric is air? Since the given dielectric is air, so it is 1. So for that unknown, we will be using this formula. C is equal to absolute permittivity times relative permittivity times area over the distance. Since the given dielectric is an air man, so this relative permittivity will become 1. So pwede na nato siya i-dili labuton. So our formula will become C is equal to absolute permittivity times area over the distance. Note that the value of absolute permittivity is 8.854 times 10 raised to -12 farad meter. So let's substitute the value to our formula. So C is equal to 8.854 times 10 raised to -12. The value of our area, which is 0.1 meter by 0.1 meter over the distance, which is 0.01 meter. So our capacitance is 8.854 times 10 raised to -12, or 8.854 picofarad. And next, if the capacitor is given a charge of 500 microcoulomb or 500 picocoulomb, what will be the difference of potential between plates? Or are looking for the voltage difference. So for this one, we will be using the formula, which is C is equal to Q over A. But then we change atong gilisan ng E o V. So our formula will become V is equal to Q over C. Since we have the value of C naman, so we will just substitute that one into our formula. So V is equal to 500 times 10 raised to -12 coulomb over 8.854 times 10 -12 picofarad. So our voltage difference for that one is 56.4716 volts. And for the next unknown, how will this be affected if the space between the plates is filled with wax, which has a relative permittivity of 4? And for this unknown, we have a given relative permittivity of 4, and we will be using this formula. So our formula is C is equal to absolute permittivity times relative permittivity times area over the distance, and our relative permittivity is 4. So that will become C is equal to 4 times the absolute permittivity times area over the distance. Since na naman tayo answer aning absolute permittivity times area over the distance, this one. So we will just substitute that one to our formula. So our formula will become C is equal to 4 times 8.854 picofarad, and our capacitance that is filled with wax is 35.416 picofarad. So it will somehow affect the voltage because the capacitance in this area is lesser, is 4 times lesser than the capacitance of this one. So we will assume that the voltage difference, the potential difference of this one, it is 4 times lesser, 4 times lesser than the potential difference of this one. So to prove that one, so we will use the formula. V is equal to 56.4716 volts divided by 4. And the voltage difference of the one that is filled with wax is 14.119 volts. So how the setup looks in actual application. So the capacitor is used not only to start the fan but also to make it spin. In other words, the capacitor creates a magnetic flux which makes the fan rotate. And for a resistor, when AC current passes through a resistor, it opposes the flow of electrons, and this property is called resistance. And for inductor, when AC current passes through an inductor, it opposes the change in current by dropping or supplying the voltage. And this opposition is called inductive reactance. This inductive reactance is denoted by letter XL, and it is measured in ohms. Since it opposes the change in current by supplying or dropping the voltage, it totally depends on how fast the current changes or its frequency. And it is given in as XL is equal to 2 pi FL, where 2 pi is our constant. Since it is directly proportional to the frequency man, so if the frequency increases, the inductive reactance will also increase. So for a capacitor, when an AC current passes through a capacitor, it opposes the change in voltage by dropping or supplying the current. This opposition is called capacitive reactance, and it is denoted by letter XC, and it is measured also in ohms. This works opposite of the inductive reactance, and it is given as XC is equal to 1 over 2 pi FC. Since it is inversely proportional to the frequency, the capacitive reactance will increase if there is a decrease in frequency. So, bali siya sa inductive reactance. So, if ang frequency mo decrease, ang capacitive reactance kay mo increase. So, and vice versa. And if the circuit is composed of the three, the resistance, the inductive reactance, and the capacitive reactance, even if the connection is in parallel or series. Since the three parameters will oppose the current in different manners, that's why we need a specific name for this opposition. And we call this property as impedance, and it is denoted by the letter Z. So, and it is measured in ohms. Even the circuit is composed only of the resistance and the inductive reactance, so or also known as the RL. So RL series circuit or RL parallel circuit. So the opposition will also be impedance sa Japon ang iyang opposition. Okay, more than one naman siya.